just some extra type. They're not types of reactions. There's just an additional part of reaction we've already learned.
If it makes you feel better, so are we taking notes on the video?
You're taking notes. You're taking notes right now. I'm videoing for the people who are taking notes. So that means that they don't have to make it the lab. They can do the lab on that night. Okay? You're making notes this weekend, but you will not do the lab. You will do the lab for class on Monday.
So we don't have to.
So you don't have to come during TL. Okay.
Oh, I'm sorry because it comes in field today.
That's okay. I know. So you're writing this down for me, everybody.
Oh, never mind. Well,
you're two people, even though you're not doing anything, let's pretend you're like it's boring.
we can just change what we're going to pretend. So we actually are. So these are all the synthesis forms. Dude, you would
no, because I did the spreadsheet for part of it. Yeah.
Yeah, I wrote it on here, but this is Oh, do you want to put PS Word out? But if you look at
Okay. Wait, you were talking about paper? What? Is the paper you wanted? Huh? The paper you wanted? Yeah.
We'll figure it out. We do have a topic, we just have to make it work. Always been fun.
time do we get in?
Alright, that should be hopefully plenty of time. We're gonna back up, so I'm gonna skip away from the slides. Being honest, a little disappointed that we didn't make progress on some of those at all. The people who tried, and even if we didn't get the right answer, I applaud you, thank you. At least you tried, and maybe who looked back at their notes? Who looked back at their foldable? Okay, who rewatched the video? Who looked online for help? I mean, there's lots of things that you can do. Who came to TLB to see Inlo? Didn't come to see Inlo, but came to TLB.
That's fine.
I'm asking. So there are things that you guys can do to fix your misunderstanding. So just the excuses of I didn't know how to do it, that's not acceptable. Okay, so I'm just going to go ahead and tell you that now. We're going to go over these instead of starting with the net ionics. There we go. And so I'm really glad we're not doing the lab now because it looks like we need to practice a bit more here. The combustion, I know I have to go over. I'm starting with single replacement here. So if you didn't do it, write it down now. Okay? If you did it, thank you. Look at problems at 11 or something if you get this because you worked hard and you looked over it. So I'm wasting your time right now. I'm not wasting your else's time who didn't do their homework. So with the original ones with the single replacements, these right here require us to use the activity series. Does everybody have one of these on their desk? Okay, so using this now, you guys tell me quickly what the reactants are. Okay, so we got that. And then your question to yourself was, is zinc more active, right? So is it higher on the activity series, yes or no?
Yeah.
Yes, so zinc and lead practically just trade places, singly replaced, and what do we get? Because zinc has a 2 charge, and Pb. Okay, what would you see in this reaction? What would this state of matter look like? This is a metal. Solid, okay? This is probably a solution that you're adding to it. I'll let you guys know that. This is just the solution that's being made. It's a product, but it's in solution, so it's kind of clear. So that's aqueous. And this is a solid because it's a solid metal. It's a metal. So whenever you see this, like you actually see zinc disappear, but then you would see lead form. Now it's hard to tell the difference because they're both just like silvery, but some things that have very specific colors, you would actually see a totally new color. So that kind of indicates to you it's a chemical change. This one's already balanced because the two's allow for that. Okay, how about I'm not going to do every single one of these, but I want to at least do 3 and maybe 5. Those of you who did it, do we have any questions on 2 and 4? The solid liquid. Only on the double replacement ones because it's very helpful on that one, but it's more to help you than to, I'm not going to take off points, it's more to help you. Okay, so looking at this one, barium mixed with water. What does the activity series say? Specifically the thing that says about cold water.
You can replace hydrogen from cold water.
Okay, so replace hydrogen from cold water, right? So I see the hydrogen here, so I know that barium will replace the hydrogen, but how does this work? I'm actually going to write water differently so you can see how the single replacement reaction works, because right here you might actually do damage by replacing both of the H's. So instead of writing water as that, I'm going to write it as H, parentheses OH, to represent H2O. So it's still H2O, but this is actually what water is made up of. It's kind of a hydroxide and a hydronium, which is this. So same story, barium and hydrogen switch places, just like any single replacement does. So what does it make? BaOH. Hold up. You still have to crisscross, doesn't matter what it is, you gotta crisscross. 2, so BaOH2 and H2, good. So this is making, what state of matter is this? Gas. You would actually see bubbles forming. You would see gas being evolving off top. So you would actually see that reaction. And then to balance it, 2 where? In front of the water, right here. So that's 2 hydrogens, 2 hydrogens, 2 OHs, 2 OHs, and a barium. So we're good there. Okay? Last one down here, 5. Aluminum is mixed with iron 3 oxide. How do you write that?
2 oxide.
What goes right here?
2.
You just cancel it. So they go, okay, there you go. Just write FeO. Okay. Because the 2 and the 2 cancel. So whenever you write like that, your job is to figure out, is aluminum more active than iron? You're looking on your list? Right, okay, so that replaces, and what do you get? Okay, so you really, really got to pay attention to crisscross charges. Crisscross charges. Don't just smush them together and call it a day. And Fe. So you would see the aluminum disappear, and you would see iron form. And you would see, it would be hard to see these change, but they do change. So this would be solid. And then what are our coefficients? Okay, and 3 up here. Okay, so I'm expecting on homework, problem set 11, that you at least write down the reactants for everything. That is nomenclature. And if you don't know how to solve for the product, then I understand, but you can at least write the reactants down. Double replacement, I'm starting with number 2. Go for it. 3, okay, because don't forget the iron has a 3 charge, and K, OH. Okay, so what happens? So basically the cations just switch partners, right? Okay. So potassium nitrate. Name that. Iron 3 hydroxide. You still got to know the charge, right? So that just forces you to crisscross it. Makes you realize that it needs to be crisscrossed. Okay, and then balance. And think of the polyatomics as a happy family. Don't break them up. So balance the polyatomics first. What's up?
I was gonna say, yeah, 3 in front of the K.
Oh, I did that one first. I thought you meant that one. So 3 in front of the K and 3 because you need 3 nitrates. Start me there. And then what? So like Alex said, 3 in front of the KOH because you need 3 hydroxides. So there's 3 hydroxides there. Yeah.
The other way around, that'd be wrong.
When you said the other way around, can you tell me specifically?
Like if you put FeOH3 in front of the KNO3.
Oh no, this order doesn't matter. It's the order inside the compound that matters. It should be KNO3, not NO3K. So yeah, it doesn't matter. What other one on the double? Oh, sorry. Actually, tell me solubility. Turn over the sheet. Solubility. Do we have anything happening? So tell me about potassium nitrate. Soluble or insoluble? Soluble. All nitrates are soluble. Iron 3 hydroxide? Insoluble because it says hydroxides are insoluble. And is iron an exception? No. It's just straight up insoluble. So you have precipitates. You'd see 2 liquids coming together and boom, you'd see a solid. Okay, so it's indicating to you that chemical reaction's happening. What other one on the doubles can I do? 4. Cobalt. 2 acetate reacts with sodium hydroxide to make what? OH2. Don't forget that it still has a 2 charge, so you gotta account for it. C2H3O2. Okay, and then balance.
The Na sodium hydroxide needs 2.
Okay, and I think it's metal. Oh no, we're here too. Right. So the 2 acetates and 2 acetates, 2 hydroxides, 2 hydroxides, everything, and 2 sodiums. Okay, and then the solubility part of this. Insoluble, because it's going to be a hydroxide, so all hydroxides are insoluble except for a couple. Acetates are aqueous, right?
Wait, so anything that has H in it is not soluble.
Anything with an OH, hydroxide, it's going to be OH. That would be considered insoluble, except for what are the exceptions for the hydroxides? Okay, so calcium, barium, and strontium. CBS is what I like to say. Those are the ones that actually are soluble. Calcium, barium, and strontium. Okay, the combustion ones I know. Those were the iffy ones people ask me about. Whenever it says combusted, what is that secretly telling you is a reactant? Oxygen, right? So there's not, I'm not going to say it. You have to know that that's what the term combustive means. So iron 2 is combustive. So iron 3, sorry. Iron 3, you still write it just as iron. Do not put the charge because it's not an ion. It's iron, it's not an ion. It's a solid. So you still write your addition of oxygen. Remember, that's diatomics, that's O2. And then it's basically like a synthesis reaction. You just crisscross them. So what do I make? And then balance. 2 here and 4 here. Okay, so that's basically, if you had some pure oxygen, you exposed it to iron, it would actually start to rust. This is rust. Iron 3 oxide is rust. So that's a real life example. That could go on your photo ball. Yeah? Okay. So this information, the word combustive just means you need to know it adds oxygen. Mercury, you can assume mercury 2 or mercury 3. Generally, it's mercury 2. That is the most common form of mercury. We'll go through that and do that one if we need to. Tell me one of the combustion of a hydrocarbon ones you want me to do. 4. So this is pentane. Pent means 5, so pentane is that particular one. Just if you want to know, it's pentane. Okay, so C5H12. What do you do with that? Add oxygen, right? The combustion ones should be the easiest ones because there's only one thing that really happens. You add oxygen and you either make it go together, or if it's a hydrocarbon, you make carbon dioxide and water. So CO2 plus water. This you just memorize, make CO2 and water. But it's nice because there's no tricks. It's just one thing. What would you need to do to balance? I hear you. Let me start by balancing my carbons and my hydrogens first. So balance my carbons on this side first. So 5 here, because I see 5 carbons there, and then, so that's 12, so I need 6 here. Okay, so then what's the number of oxygens here? 5 times 2 is 10 plus 16 oxygens, and that's an even number, right? So I know I can put a number in front of oxygen here, that gives me 16. 8. None of that doubling stuff. It's just what it is. So 1 to 8 to 5 to 6. If you did double everything and you look back at your coefficients, you're like, oh man, they're all even, then you'd have to reduce them all to the lowest ratio possible. So that's easy to do after the fact. Okay, yeah. Questions are here. Do you feel comfortable doing that now? Yeah. Any hydrocarbons, anes, and ions, alcohols, benzene rings, anything that's a hydrocarbon just means H's and O's, or H's and C's together. Or like glucose with HC though.
Is number 2 Mg2O2?
Mercury is Hg. I knew what you meant though. And
Well, no, it'd just be HGO.
HGO, and then you put a 2 here and a 2 here. Okay, so now I'd like to go ahead and just introduce you to NIEs, which are net ionic equations. I'm going to let you watch a video on it first. This is something that you just wrote down on here. Nope. Here. Did we get to write this down? Okay, so I'm going to show you a video first, and so this guy showed you how the net ionic equation works. Basically, we know that when molecules and ions go into solution, sometimes they're just free floating around, sometimes they're absolutely doing nothing, which is a no reaction. Sometimes they clump together and they form a precipitate, or they form a gas, or they form something else. So to really look and see what's actually happening, you have to consider the net ion equation, which is what's happening versus some other stuff that are just spectator ions. So what does it mean to be a spectator, by the way, like a sporting event?
Like you're just watching.
You're just watch. Do you play? No. Okay, you get in trouble if you get on the field, right? So you don't do anything. You simply watch. And that's the same thing as ions. Ions sometimes just watch the reaction while other things are participating or precipitating, like I like to say, because these are going to be mainly dealt with in double replacement reactions. So let's go ahead and watch our quick video, and then we will talk more. Oh, wrong video too. Wrong. There we go. Mr. Anderson.
This reaction. So in this reaction, we're taking lead nitrate, which is clear, and we're adding it to a solution of potassium iodide, and it produces a yellow precipitate. And so what we're getting is a solid that comes out of that. And so I could observe that. I could know what those chemicals are, and then I'm going to write it out. So we've got a solution of lead nitrate, solution of potassium iodide, and it's making a yellow precipitate of lead iodide that settles to the bottom. Next thing I want to do is I want to write out my reactants and products. Now,
Go ahead and write out your reactants according to what the reaction is. Everybody's writing this down. This will be a good example. So tell me what you're writing.
PB, single three,
Uh-huh. PB unit 3, 2, plus
K,
K,
I,
I. Okay. Then he's going to tell you. Oh, he says the precipitate of lead 2 iodide. He didn't write 2, but it's lead 2 iodide.
if you don't know how to write, go from the name of a chemical to its equation and vice versa. I'll put a link down here to a naming molecules or a naming compounds video that should help out. So the first thing I want to do is I want to write out all the reactants and products. So now we've got lead nitrate, potassium iodide, making lead iodide and potassium nitrate. Next thing I want to do is I want to make sure that I balance it. And so I can see right here that I don't have enough iodine on the left side, so I could add a 2 there. Now I've got too many nitrates on the left side, so now I can balance it like that. I also have to write the state that it's in. So remember, those first 2 were aqueous, but this lead iodide is going to be a solid. And now I've got a nice molecular equation. But again, this video is about 2.
So he's basically already did the solubility rules. We know how to do that though. So heavy metals, the iodides, they do precipitate out. Everything else is aqueous though, so that just means mixed with water. This one is a solid. We cannot ionize it. We'll talk about, he's going to talk about that here.
2 other equations. We've got ionic equations and then net ionic. And so how does that work? What is an ionic equation? Well, if you think about this lead nitrate right up here, it's not sitting in that solution as a connected molecule. Remember, it's going to break apart into its ions. It's going to have its lead ions and nitrate ions, and those are going to disassociate from one another. Those are going to separate from one another. And so when I'm writing out an ionic equation, what I have to do is I have to write out all the ions. And so let's do that one first. I'm going to have that lead ion, which has a 2+ charge, and then 2 of those nitrates, which have a 1- charge. Now, why am I writing a 2 here? Because we have 2 of those nitrates. And so you can see in an ionic equation.
So when we ionize things, we simply take the ionic compound and we basically uncrisscross. So it's showing how it actually acts in solution, because sometimes things solidify and we can't break them up, period. This doesn't happen. But if they're ionic and they're soluble, it means that they will dissolve, they will ionize, they will separate. So that's why you put the Pb2+ and then the nitrate, but the nitrate, there's a 2 subscript outside of it, so there's that indicates there are 2 of them. So there's another coefficient here. So we're basically undoing what we kind of did already.
Equation, what I'm doing is I'm busting apart each of those ions. Let's go to the next one. So that potassium iodide, I'm going to break that apart into its 2 ions as well. You can see that I'm writing that this is in solution, so it's aqueous. Next we get to the lead iodide. Now remember that lead iodide is a solid, it's that yellow solid, and so I'm not going to bust that apart into its ions, I'm just going to write that as lead iodide as a solid. But then this potassium nitrate is going to break apart into its different ions, so I'm going to write it out like that. So I know that's a lot of work, but this is a complete ionic equation. Why is that important? It really allows us to look at what ions are in that reaction. So if it's ever an aqueous reaction, lots of times we'll use this ionic equation. Sometimes they'll call it a complete ionic equation because it's showing all of the ions that we have present. Okay, what's the...
So looking at this equation now, you actually can tell who are the main players. Who are the main players in this reaction? Remember, reactions are based off our evidences of chemical change. So what is the chemical change that's happening? It's precipitating out, right? So we have lead 2 iodide that's precipitating out. So who are the players that make that happen? Who are the players that make that right there happen? No, they're not involved at all. Who makes this is what I'm asking. Lead 2 and the iodide. Those are the main players. What are the rest of these people doing? Nothing. They are spectating, they are watching, they are simply there because I can't add straight lead to a solution. I can't add straight nitrate to a solution. I have to add lead to nitrate because that's how this comes. They come in compounds. They don't come as individual ions. So I add it together with the with the potassium iodide, but potassium and nitrate, they don't do anything. They don't do anything. They are just sitting there watching. That's
third
called
type of
spectators.
equation. That's going to be the net ionic equation. So if we look back at this equation, you can see that we have 2 nitrate ions on the left side, and we also have 2 nitrate ions on the right side. And so they're really not being changed in this reaction. And so we call those spectator ions. They're really just watching. And so what you can do is you can cross out things on the left side that are also found on the right side, as long as they're in the exact same form. Can you find something else on the left side that's also on the right side? That's going to be those potassium ions. So I could cross those out as well. And so once I've crossed out all those spectator ions, I can write it out like this, and that's going to be my net ionic equation. So that's really, it's just showing what atoms are part of this chemical reaction that are actually forming these bonds. And this will become important when we're looking at redox reaction.
Okay, take a break, stand up. I know you need to. And we're going to go through a couple of examples. We're not that one because we just did that one.
No, we're supposed to done, guys.
Are they always that big?
What?
The big reaction?
Yeah.
Well, it looks really big because we actually have to separate them, and so it makes it take up a lot of space. So at some point in time, you will get to the point where you're like, I know how to do this, and you can skip this step. But I would recommend, you're going to be writing these out quite a bit. Okay, watch that come. I know, there's only a couple people left. All right, come back to me now. I want to do at least 1 or 2 examples with you, and then we'll be done. I've already done 1 example. This should be on your paper. Is this on your paper? It is. This is the first example. I'm not doing it here because I did it here. Same thing. Okay, next one. You guys write out the reaction first. BC, go. Write it out. And since we're downstairs, we just leave a little later. Oh, sorry. Alright, so 125, we got band going, ball athletes and dance class participants, football, men's soccer, women's tennis, volleyball, cross country, women's golf. And then we as a class will go at 140. Men's soccer? Yes? I don't think, do we have any other athletes? Oh yeah, cross country, yeah, that's right, I knew that. Okay, what's your reaction then? Reaction. CL2, the more you participate, the less we precipitate, right? Sodium. 3. Okay, makes what? Mg3, PO4, 2, and NaCl. So you're switching them, you're crisscrossing like a boss, then you're balancing. Yes. I see 2 chlorides. What do I need here? 2. Ooh, maybe. Sorry. I see 3 sodiums. How do I make this 3? I mean, how do I make a combination of 2 and 3? I make 6. Sorry, this is a 6. I just want to go and point that out to you. So 6 sodiums here means I need to put a 2 here and a 3 here, and that satisfies my magnesium of 3, and that satisfies my phosphate of a 2. So we can balance. Next step, so we just did our BC, we did our balancing, I'm sorry, which is the BC. We look at our solubility. What is the problem here? Who's our precipitate? Look at your rules. Phosphate, because what? Because why? All phosphates are insoluble. Okay, so this was our precipitate. What about sodium chloride? Okay, so as we go through now, we know who to keep together. I'm actually going to put a little box around this to tell you to keep together. Don't mess with it. Leave it as it is. The rest of these must be ionized by splitting them. So I have 3 magnesium ions. What's the magnesium ion? Say again? 2 plus. That 2 comes back to magnesium. I have total of how many chlorines? 6 chlorines. And that chlorine has a charge of what? -1. Good, I heard you. So that's 6 and that has a -1 charge. So we're basically splitting this up at distributing the coefficients. Okay, so that one's been taken care of. Plus, how many sodiums? 6 sodium. And what's the ion charge? +1. And how many phosphates? No? No, there's a 1 out here. 2. There's 2 phosphates. You guys can finish watching the rest of this video later. 2 phosphates. And then what do you do with this? You keep it. You leave it alone. You just simply move it down. And then what do you do with this?
No, you cancel the.
Hold on. What do I do with this first? 6 Na what? Plus, if you don't write the charges, then that's going to cause problems later on when we're trying to try to cancel. And then 6 chlorine ions, chloride ions. Okay, so now that we've simply broken them up, all except for the precipitate, now your job is to figure out who looks exactly the same in the reaction, meaning they didn't do anything, they didn't react. So this, I heard 6 Cls first, 6 Cl minuses, and 6 Cl minuses. It has to be exactly the same to the charge and everything. And 6 sodium 1 pluses, good, 6 sodium 1 pluses. So what do you call those? Spectators. They're spectator ions specifically. And then we rewrite this to show the appropriate NIE. So the NIE, the net ionic equation, is 3 Mg2 plus, because it didn't get canceled, 2 phosphates yields this guy, Mg3 PO4 2, magnesium phosphate. So I know it's extra steps, and it looks really complex. So do you know your 3 big steps to how to do this? Now that you know how to write balanced chemical equations, you know how to predict products and everything. It's just an extra addition. And so we have to do this in honors chemistry, and this is a definite thing in AP chemistry. So we have to do the whole gamut. So the first step you do is what? Okay, so first thing you do is write the reaction, and then you figure out the solubility, and then do what? Ionize, and then so cancel the spectators, and then just rewrite it. Okay, so what I want you guys to start on is this weekend to try to do problem set 11 where those problems come in. You can do like 90% of problem set 11 except for the things that says NIEs. You can at least start it now because you guys know what's going on. Then you have to do on Monday. Okay, so for the last 10 minutes or so, if your Mythbusters buddy's here, you talk to them. If you have a PS 11 question, come ask me. If you didn't do your 15 questions for homework, then now we sit there and do those now. Okay? We did some of them in class. You can finish them up. Other than that, you guys are good. We have 10 minutes left.